The Magellanic Clouds are two patches of light that you can see on a really dark night in the southern hemisphere. They look like pieces of the Milky Way that somebody tore off and threw to the side. Really, they're two neighboring galaxies caught by the gravitational pull of our own galaxy. If we zoom in on a seemingly random part of the large Magellanic Cloud, we find what looks like a necklace of luminous pearls, along with two fainter rings to the sides. It's beautiful, but what is it? Our story begins on February 22nd, 1987. Ronald Reagan is President of the United States. The Iran-Contra affair is coming to a boil. Tonight on TV are new episodes of Family Ties and Murder, She Wrote. And someone pointing a telescope at this part of the Large Magellanic Cloud would have seen a star named Sanduleak 69-202 with only one day to live. It's a star of nearly 20 solar masses that was shining for 10 million years. Then the core ran out of hydrogen and started contracting, surrounded by a shell of burning hydrogen. Soon, the core became hot and dense enough to fuse helium into carbon. The helium lasted 500,000 years, but eventually the core was completely converted into carbon and oxygen, surrounded by a shell of burning helium, which was itself surrounded by a shell of burning hydrogen. The core contracted enough to ignite the carbon, but fusing heavier elements doesn't produce as much power. The nuclear binding energy curve starts flattening out as you approach the peak. So the supply of carbon lasted only a few hundred years. The core contracted some more, igniting heavier elements, getting ever denser and hotter, the ashes from one reaction serving as the fuel for the next one. The core started to look like an onion with concentric shells of fusion. After just a few years, the core worked its way up to silicon, forging it into iron. This last, most desperate phase of fusion lasted only one day, today. Now the core is nearly all iron, one of the most stable nuclei. Fusing iron doesn't release energy, it requires energy, so there's no more nuclear power available to prevent the core from gravitational collapse. And despite shedding lots of material up at the surface from the star's radiation pressure, the core is still more massive than the Chandrasekhar limit of 1.4 solar masses, which means electron degeneracy pressure is powerless to prevent collapse. So the floor drops out. All the material in the core falls freely toward the center. A few lectures ago, we calculated the free fall time, the time it would take for a sphere to gravitationally collapse to zero size. It's on the order of the square root of r cubed over 2gm. Plugging in 5 solar masses for m and the size of the Earth for r, roughly the dimensions of the core, we get half of a second. An Earth-sized object vanishes in the wink of an eye. But that wasn't the end. You see, the star didn't just collapse to form a black hole. For reasons we'll explain later, it exploded, releasing a staggering amount of energy. This kind of event, a core collapse supernova, only happens about once per century in a galaxy like the Milky Way. So as you might imagine, the astronomers of 1987 were very excited to see one so relatively nearby. They observed it at all possible wavelengths over many years. This allowed them to estimate the total energy released by the explosion in all detectable forms: light, X-rays, the kinetic energy of the shock waves that slammed into the surrounding gas, and so on. They came up with a figure of order 10 to the 44 joules. Astronomers had already seen lots of core collapse supernovae in more distant galaxies, not in nearly as much detail, but the total energy always tended to be of order 10 to the 44 joules. 10 to the 44. Let's try to put that into perspective. Remember when we calculated the lifetime energy output of the sun by multiplying the sun's luminosity by its age? The answer we got was 5.5 times 10 to the 43 joules. So within a few seconds, a core collapse supernova releases about as much energy as is radiated by the sun over billions of years. And that's not all. A core collapse supernova releases even more energy in a hidden form. By 1987, experimental physicists had built a new generation of underground high-energy particle detectors, huge vaults of liquid surrounded by equipment that can spot the tiny flashes of light that happen when a high-energy particle makes a rare collision with an atomic nucleus somewhere in the liquid. These new detectors were not all designed to study neutrinos. The new purpose was to measure the decay of protons, which, if it happens, would produce high-energy particles that could be detected. Protons are very stable, but some of the particle physics theories that were then in vogue predicted that very rarely a proton would decay. None of these experiments ever spotted a decaying proton, but some of them did detect a burst of high-energy neutrinos on February 23, 1987. The total number of neutrino detections that could be attributed to the supernova was about 25. 25 teensy-weensy little particles doesn't sound like much, but after correcting for how many neutrinos weren't detected because they sailed right through the Earth, physicists estimated that the total energy of all the neutrinos produced in the supernova explosion was of order 10 to the 46 joules, 100 times more than all the light and the heat. This teaches us that we should think of a core collapse supernova as a neutrino explosion, which as an incidental byproduct produces a small fireworks display. Where do all those neutrinos come from? Well, whenever you see neutrinos, you know the weak nuclear interaction has been up to something. What happened in Sanjulik minus 69202, and what happens in all core collapse supernovae, is that the core of the star contracts so much that the positive ions and the negative electrons are crushed together, packing so close that even the weak interactions with their very short range can mix them up and transmute them into neutrons. As it turns out, the endpoint of these transmutations, the most stable mixture at these very high densities, is mainly neutrons, with only a minority of protons and electrons. So the star becomes a neutron star. When nucleons are pressed together tighter than a femtometer, the strong nuclear interactions also become important, and they prevent further compression. Remember when we conceived of a nucleus as a cluster of rigid marbles? Well, a neutron star is a cluster of 10 to the 57 marbles, and the gravity is so strong that those marbles are noticeably squished. If the mass of the collapsing star is too large, if it's more than about 2 solar masses, the marbles shatter. The strong force gives way, and the core collapses all the way to become a black hole, a point with zero volume endowed with the mass of the star. But if the core is less than 2 solar masses, the strong force is just strong enough to prevent this fate. That's when you get a neutron star. We can estimate the size of a neutron star by analogy with our earlier work on white dwarfs. What we did then was to set the pressure required for hydrostatic balance equal to the pressure from electron degeneracy. That led to a relationship between mass and radius, with radius being proportional to 1 over the cube root of the mass. That formula for the radius has a factor of the electron mass in the denominator. That traces back to our decision to consider only the electrons and ignore the degeneracy pressure from the nucleons, which made sense at that time because degeneracy pressure varies inversely with particle mass, and a nucleon is 1,800 times more massive than an electron. But if most of the electrons are gone because they merged with the protons, then it's the neutrons that provide the degeneracy pressure. If we repeated our calculation for neutron stars, what would happen is that the electron mass in the denominator would be replaced by the neutron mass. The consequence is that the predicted radius is lower by a factor of 1800 for a given mass. We saw that electron degeneracy leads to stars the size of the Earth, which has a radius of 6,400 kilometers. Neutron degeneracy should then lead to stars with the size of just 3 or 4 kilometers. Now, although this line of reasoning does give the right order of magnitude, in reality, most of the internal pressure in a neutron star is from the strong nuclear force, not just degeneracy pressure. That's something we didn't have to worry about for white dwarfs, but for neutron stars, it's a big worry, and it makes calculating the mass-radius relationship very difficult. Most theorists who have tried arrive at a radius in the neighborhood of 10 kilometers for a neutron star with a typical mass of 1.5 solar masses. 10 kilometers is an unusually easy figure to relate to in astronomy. That's the size of a small city, or the length of a 10K race, a 6-minute drive on the highway. What is much harder to relate to is that this city-sized object packs the mass of 1.5 suns. When we first encountered white dwarfs, we marveled at their high densities. 1 cubic centimeter has the mass of several metric tons. Well, a neutron star has a comparable mass and radius 1,000 times smaller, so the density of a neutron star is higher than that of a white dwarf by a factor of 1,000 cubed, a billion. A cubic centimeter has the mass of 1 billion tons. Imagine digging into the Earth's crust and cutting out a chunk that's 1 kilometer on each side, a cubic kilometer of rock. That would have the same mass as a typical spoonful of neutron star material. Does that help to put it into perspective? I'm not sure. Analogies simply fail us for neutron stars. There are too many orders of magnitude between us and them. Maybe more helpful is to remember something else I said about a white dwarf. It's sort of like a giant stellar mass atom, in the sense that the electrons are pressed so closely that the Fermi exclusion principle comes into play. Well, a neutron star is like a giant stellar mass atomic nucleus. It's thousands of times smaller than a white dwarf for the same reason that the nucleus of an atom is thousands of times smaller than the electron cloud. Another comparison we can make is between the size of a neutron star and the size of a black hole of the same mass. Now, strictly speaking, a black hole has no radius, but I'm talking about the Schwarzschild radius, 2gm over c squared. The Schwarzschild radius of a 1.5 solar mass black hole is 4.4 kilometers. That's not that much smaller than the 10 kilometer radius of a neutron star. So we conclude that a neutron star is right on the verge of becoming a black hole. Compress it by a factor of 2 or 3, and poof, it goes black. I find it remarkable that the strong nuclear force comes to the rescue just before the star collapses to become a black hole. Had the strong force been just a little weaker, or gravity a little stronger, there would be no neutron stars, no core collapse supernovae, which would be very upsetting because, as we'll see shortly, core collapse supernovae are the source of many of our favorite elements in the periodic table. Let's go back to imagining the collapsing core. The core is now compressed to nuclear density, and even a little beyond, until the strong force provides enough rigidity to halt the collapse. But there's still several solar masses of material in the outer layers of the star, material that is now falling directly onto the surface of the newborn neutron star. So bam, it rebounds from the surface, producing a shock wave that travels out at thousands of kilometers per second, driving that gas outward. This produces a lot of heat and a burst of nuclear reactions. And these reactions are not like the steady reactions at the center of the sun, which gradually work their way up to heavier elements over billions of years. No, These are sudden, violent, uncontrolled reactions that reach all the way up to iron and even a little beyond. The elements that are forged range across the periodic table from carbon, nitrogen, and oxygen up to yttrium and zirconium, and the explosion sprays them all over the galaxy. Let's estimate the total energy of the explosion. Ultimately, it comes from the release of gravitational potential energy when material collapses onto the core. So we need the formula for the gravitational potential energy of a sphere. A sphere that contracts from some very large radius to a radius r will release an energy of 3/5 gm²/r. That energy is converted into the other forms, the neutrinos, the shock waves, the light, and the heat. If we put in 1.5 solar masses for m and 10 kilometers for r, the number of joules comes out to be of order 10 to the 46. That's compatible with the neutrino observations that I described earlier. It's a pretty good check on our understanding of supernovae. Of course, even better would be to see the neutron star itself. A neutron star is born at a temperature of hundreds of thousands of degrees. That's so hot that there's hope of detecting its thermal radiation, even though it's so tiny. Astronomers have pored over the spot where Sanjulik -69-210 used to be, but so far they haven't seen any neutron star. Nobody knows why. Probably it is there, but it's obscured by the material surrounding it. It'll be easier to search once the surroundings have cooled down and cleared out, in a few hundred years. Fortunately, in the meantime, we can look at the aftermath of a supernova that did occur a few hundred years ago. Cassiopeia A is the fading remnant of a supernova explosion from the 17th century, although nobody seems to have noticed it at the time since it's behind some thick clouds of dust in the Milky Way. But we can see it now clearly in X-ray images, which show all the gas that was pushed out into space and heated to hundreds of thousands of degrees. And right in the center is a tiny dot, representing the X-rays from the neutron star. The Crab Nebula, 6,500 light-years away in the constellation of Taurus, is a different kind of supernova remnant. The neutron star isn't just quietly cooling off. It's ejecting energetic particles that energize the surrounding gas, producing a bluish-green haze that permeates the nebula, along with lots of X-rays. The history of the discovery of neutron stars is very interesting. The neutron, the particle itself, was discovered by physicist James Chadwick in 1932. Just 2 years later, astronomers Walter Baade and Fritz Zwicky dreamt up the idea of a neutron star and proposed that a supernova is the transformation of an ordinary star into a neutron star. They performed the same order of magnitude calculation that we did, showing that this transformation would release 10 to the 46 joules. And then, in 1967, neutron stars were detected. It was a triumph of the scientific method and human imagination. An exotic, hypothetical state of matter is predicted and then observed in nature. But the story isn't quite so simple. The way in which neutron stars revealed themselves hadn't been anticipated by anybody and remains to this day a poorly understood phenomenon. They pulse. Jocelyn Bell, now Bell Burnell, and Anthony Hewish discovered radio sources that emit regular pulses like a clock. The Crab pulsar, for example, emits a pulse every 33 milliseconds. What we think is happening is that the neutron star is shining narrow beams of radiation from points on its surface, probably the 2 points along the axis of the star's magnetic field. And the magnetic axis need not be aligned with the rotation axis. So as the star rotates, the beams of radiation swing around like the beam of a lighthouse. And if one of those beams happens to sweep across the Earth, we see a pulsar. You probably have a lot of questions. What causes the beams? Why are they misaligned with the rotation axis? I don't have any simple answers for you. The proposed mechanisms rely on concepts from plasma physics and they're topics of ongoing research. But there's one question I can answer. Why do neutron stars rotate so darn fast? The sun only rotates once a month. White dwarfs tend to rotate once a day or so. But the Crab pulsar spins around 30 times per second. Try to imagine that. A city-sized sphere, more massive than the sun, spinning as fast as the tires of an Indy 500 race car. The reason neutron stars spin so fast is the conservation of angular momentum. The angular momentum of a spinning body is I times omega, where omega is the angular frequency, how many radians per second, and I is the moment of inertia, which is mr squared times some constant that depends on how the mass is distributed. For a sphere of uniform density, the constant is 2/5. Before it collapses, the core has a radius r initial and spins with an angular velocity of omega initial. Then gravity compresses the core to a radius r final. What happens to the angular velocity? We can figure that out by appealing to the conservation of angular momentum. During the collapse, the star doesn't lose any mass and it's not getting torqued from outside, so we can equate the initial and final values of r squared omega. Therefore, omega final over omega initial equals the square of r initial over r final. Since r shrinks by a factor of 1,000, the angular velocity increases by 1,000 squared, or a million. So a rotation period of 1 day becomes a period of 100 milliseconds. Another interesting thing is that if you observe a pulsar for long enough, you'll usually see the rotation is slowing down ever so slightly. Every year, the Crab pulsar's rotation period grows by 13 microseconds. If it's slowing down, it must be losing energy. Let's figure out how much. The kinetic energy of a rotating object is 1/2 I omega squared, which we can write in terms of the rotation period using omega equals 2 pi over p. If p changes, then E must be changing. So let's take the time derivative to see the connection. Then, let's plug in the parameters of the Crab pulsar. M is 1.5 solar masses, R 10 kilometers, and P is 33 milliseconds. dp dt, the slowdown rate, is 13 microseconds per year. After converting the units and multiplying through, the answer is 5 times 10 to the 31 joules per second, which is a good match to the observations of the total luminosity of the Crab Nebula. So what's happening is that the rotating pulsar is flinging away high-energy particles from its surface, which fly off and light up the surrounding nebula. The neutron star is acting like a giant flywheel, a reservoir of rotational kinetic energy that's being tapped to light up the surrounding gas. In that sense, the Crab is a rotation-powered nebula. Once the period and the period derivative have been measured for a pulsar, that's usually enough to predict future pulse times very accurately. In that sense, pulsars make good clocks. In fact, some pulsars rival the accuracy of the world's best atomic clocks. Now imagine you're the sort of astrophysicist who loves very precise measurements. You wish you could launch a bunch of atomic clocks into space, all equipped with radio antennas, so that they could broadcast precisely timed radio pulses, like a GPS system for the galaxy. You'd be able to track those clocks with phenomenal precision by measuring the pulse arrival times. If the time between the pulses is growing more than expected, you would know the clock is accelerating away from you. Each pulse of radio waves has a longer distance to travel than the last one, and vice versa. When the pulses arrive closer together, the clock must be accelerating toward you. Well, Mother Nature must like precise measurements too. She provides us with a category of pulsars called millisecond pulsars, which spin unusually rapidly, even for neutron stars, and are incredibly stable. By timing them, we can measure all sorts of subtle physical effects, including the slight warpages of space and time predicted by general relativity. There's also one spectacular case of a pulsar for which the pattern of pulse timings revealed 3 planets going around it. The pulsar is moving around the center of mass of a planetary system. Why are there planets around a pulsar? Wouldn't they have gotten annihilated by the supernova? Yes, they would have. So the idea is that the planets there now probably formed after the supernova. They might have formed out of material that fell back toward the neutron star, forming a sort of zombie protoplanetary disk. Before I bring this lecture to a close, I want to bring up a confusing subject, which is the nomenclature of supernovae. It's confusing because, as in many cases, the phenomena were named and classified long before they were understood. Originally, the word supernova simply meant a really energetic explosion, to be distinguished from a nova, a milder but still very impressive explosion. Then, over time, different flavors of supernovae were recognized. The spectrum of the explosion at its brightest phase sometimes reveals evidence for hydrogen. Others have no hydrogen. Those without were called type 1 supernovae, and the ones with hydrogen were called type 2. Then the type 1s turned out to show some variety too. Some of them have lots of silicon in their spectra, others not so much. So type 1 was subdivided into 1a, 1b, 1c, and so on, depending on which elements were on display. Now, wouldn't it have been convenient if type 1s all turned out to have the same physical origin, and type 2s had a different origin? Well, Mother Nature didn't read the memo about our classification scheme. The most meaningful physical distinction is not between type 1 and type 2, but between type 1a and everything else. The phenomenon we've been discussing, the transformation of an ordinary star into a neutron star, is a core collapse supernova, which can be type 2, 1b, or 1c, depending on the details of how the massive star shed its outer envelope before the core collapsed. As for type 1as, they have a fundamentally different origin, one that's less well understood. All the theories involve a white dwarf that, for one reason or another, became too massive for its own good. One way this might happen is accretion-induced collapse. In this scenario, the white dwarf has a companion star which has evolved into a red giant. The giant star gets so big that it runs afoul of the Roche limit. The tidal forces from the white dwarf tear away the giant's weakly bound outer layers, and the torn-off material forms a vortex around the white dwarf, an accretion disk. And ultimately, the material crashes into the surface, increasing the mass of the white dwarf. The white dwarf accretes mass from the companion star until it approaches the Chandrasekhar mass and starts collapsing. But instead of becoming a neutron star, in those circumstances, it becomes hot and dense enough to ignite the carbon and the oxygen inside, detonating the entire white dwarf in a sudden thermonuclear blast. An alternative idea is a white dwarf merger. In this scenario, the companion of the white dwarf is another white dwarf. After billions of years of peaceful coexistence, the two stars merge, and their combined mass is high enough to precipitate the nuclear blast. Now, why would they merge? One reason is that the orbit gradually loses energy by radiating gravitational waves, the topic of the next lecture. That would cause the white dwarfs to spiral toward each other. Or, if the two white dwarfs are part of a triple star system, the complex three-body gravitational interactions can sometimes lead to a head-on collision between two stars. Regardless of the explanation, the striking thing about type 1As is that they all have nearly the same peak luminosity. They're much more standardized than core collapse supernovae. That's what makes type 1As useful for measuring the distances to faraway galaxies. They function as standard candles or standard explosions. You measure the maximum flux, you can infer the distance. This commonality of type 1As might be because the exploding mass is always nearly the same, the Chandrasekhar mass. Type 1As also leave behind remnants that are just as impressive as core collapse supernovae. They're among the most beautiful images ever made with X-ray telescopes. Among the most well-studied are Tycho's supernova remnant from an explosion that was recorded in 1572, and another one called Kepler's supernova from 1604. It was just a few years after that one when Galileo pioneered the use of the telescope for astronomy. So it's a little annoying that since 1604 there haven't been any other supernova explosions detected in our own galaxy. We're overdue for one. The one in 1987 was nearby in the Large Magellanic Cloud, but it would be even more revealing to be able to study one closer to home. Not too close, of course. Imagine what it must have been like in 1054, when Chinese astronomers noted a brilliant new star in the sky, shining brightly enough to see during the day. They were careful observers, but of course they had not the slightest clue what they were observing. They interpreted it as an omen. Imagine if we could tell them that what they were seeing was the light from an explosion that took place 6,500 years earlier. That for a few seconds the explosion was more luminous than 1 billion suns, and that most of that energy was released in the form of invisible particles. That the omen was the collapse of an object more massive than the sun, compressed to the size of their capital city, and spinning 30 times a second. It makes you wonder, what phenomena are we observing today that we don't fully understand, that will someday, maybe 1,000 years from now, teach us such incredible and fascinating things?